Hello, and welcome back to the Fabric of Industry podcast, episode 3, Mining. I am your host, Adam Grange. This will be a longer episode than the previous, because I have a lot to discuss, and also in part because this is more where my expertise and studies lie. We have so far covered the agricultural, forestry, and fishing industries on a foundational basis, and will now simply be looking at mining. Yet it is anything but simple. Prerequisite for this episode would be episode 1, at least the first half of it. What is the primary sector? Because it lays down some foundational topics, such as the Human Development Index, that will be used later in the episode. The other 3 industries in the primary sector I have discussed are not necessary to understand the context of this episode, but I believe it is best to have a grasp on all of the industries in the primary sector to fully understand it. As I said, I have a lot to cover, so strap in. I'd like to provide a foundation for what the categories of major minerals and resources are, such as metallic ore, and then what resources are actually contained in those categories, just as some examples, such as iron, and then discuss what mining actually is and the machinery used in the various practices. As per usual, I will also be discussing the economic importance of mining and briefly about the technological advancements made in the industry, as well as the environmental impacts, since this could potentially be considered the most environmentally destructive primary sector industry. I'll touch on some ethical and social issues as well, though mostly in underdeveloped countries, as I brought up within the forestry industry last episode. If I have time near the end, I'd like to quickly discuss some governance and regulation surrounding the industry, as well as the historical and cultural context, or I might put that somewhere else in the episode, depending on how it flows, and then some case studies throughout, and I'll bring up the mining and energy paradox as well. This may be a bit ambitious, and if I'm running too long and have enough content, I may split this in 2 episodes, but we'll see. Anyway, let's jump into it. I think it will be best to lay a foundation in minerals first, as I said, without getting too far into the chemistry of classification. Essentially, minerals are organized using their dominant anion. An anion is the negatively charged element in a chemical composition of something. It doesn't necessarily have to be an element, but that's a single element. And the positive portion is called the cation. We've probably all heard, hopefully, of positive and negative charges, and perhaps you remember electric charges of atoms from high school chemistry or something. Electrons are the particles in an atom that will mostly distinguish electrical charge. Protons have a positive charge, electrons have a negative charge. It's a bit arbitrary, but that's getting too deep into chemistry, for at least this episode. But electrons are the ones that distinguish the electrical charge of a specific element, because if you change the proton count, then it changes the type of element it is. So you can think of an anion as the atom gaining electrons, and a cation as the atom that loses electrons, because if an anion is gaining if an atom is gaining electrons, then it gets higher in negative charge, and so it becomes an anion, and vice versa for a cation. And this is, of course, when atoms bond together, when elements bond together. This is only one type of bond, however, and it is known as an ionic bond because it creates ions, hence the anion and the cation. A chemical bond is how atoms stay together and form different compounds that we may be familiar with, such as table salt, which is an ionic bond between one sodium atom and one chlorine atom, which is actually a relatively interesting case, but I won't get into that. Typically, an ionic bond will be between a metal, which forms the cation, because it loses electrons, but it can be a non-metal too. And then it's usually bonded to some highly reactive element on the right side of the periodic table, which the periodic table is how we organize the different elements. And that forms the anion because it gains electrons, so it becomes negative. An anion can also be a separate group of bonded atoms that form a full compound with a negative charge, called an anionic group. So, like I said, it doesn't necessarily have to be a single element that is just the anion. It can also be multiple elements bonded together, and that forms an anionic group. And that can bond to a cation. This is important for mineral classification because sometimes a mineral will be a metal bonded to a single type of anion, such as oxygen, or a mineral can be a metal bonded with an anionic group, such as a silicate, which is just the name for a group of anionic compounds that bond to cations. Of course, it doesn't always have to be metals, but a lot of the times with minerals, especially minerals we're interested in, they're going to be metals. There are currently 11 divisions of anions or anionic groups used to classify minerals. Each of them aren't necessarily important for our discussion here, and it will be difficult, I imagine, to remember all of them through just my voice talking, but here they are. We have native elements, sulfides, sulfosalts, oxides, hydroxides, halides, carbonates, nitrates, borates, sulfates, phosphates, and silicates. A lot of eights. I'll go, of course, not the number 8. It's ATES. Anyway, I'll go in order of how I just said them to explain them a little bit. Some of them are going to be a lot more important than others. Native elements as a group kind of go against what I just said earlier in that minerals are classified by their anion or anionic group because native elements are minerals that just occur by themselves as one element. So they don't have a cation and they don't have an anion. They're kind of the special case. They're not bonded to anything else. They're relatively rare, and it usually includes metals that don't very readily react with other elements, such as gold or silver. And some semi-metals, or we call them metalloids, are also found natively. These are in between metals and non-metals. They have properties of both. And they include things like antimony, which are used in batteries a lot, and arsenic, which you may have heard of before. But the reasons why an element is called a metal or a metalloid or a non-metal isn't that important for this episode. Native elements can also be non-metals, and the most common is carbon. You can think of diamond, as it is purely made from carbon. The second group is sulfides, and these are described as minerals with sulfur bonded to one or more metals. Common metals found in the sulfide compounds include iron, copper, nickel, and lead. Maybe you've heard of lead sulfide before. That's just PBS. That's all it is. Well, it's a little more complicated than that, but on a basic level, that's all it is. The third group are sulfosalts, and these are by far the most complex mineral type in how they are composed, but they are rather rare, so they aren't typically mined very often. And understanding exactly how they're formed and how they work isn't too necessary. Maybe I'll do an episode diving super deep into minerals and chemistry at some point, because I am very interested in that kind of stuff too, but for a foundational episode in mining, it doesn't really matter too much. Oxides can be grouped into simple and multiple oxides, but they are essentially oxygen atoms, various amounts, bonded to metals. These form very commonly in what we refer to as ore deposits, and therefore they are what is commonly mined. There are other types of ore, but oxides are very common. This is because many metals readily form bonds with oxygen, including iron, zinc, manganese, aluminum, and chromium, all of which have extensive industrial applications. Hydroxides are the group where a hydroxide ion, which is a negatively charged compound of one oxygen and one hydrogen with a negative charge of 1, -1 is the charge on it. The hydroxide ion bonds usually to a metal, but it can be an organic group too, though that doesn't really matter too much for mining. Hydroxide commonly bonds to sodium, aluminum, and magnesium. Halides are another relatively rare group that is described as a salt of a halogen acid. This is probably not a very clear description, and explaining it would take the rest of the episode, so just accept it for now, because they aren't too important for mining anyway. Common halides include halite, or rock salt, which you may have heard of, sylvite, and fluorite, which you also may have heard of. carbonates, or specifically carbonate minerals, since there are carbonates in chemistry outside of mineral classification, are a very, very common mineral group. A carbonate ion is a compound with a negative charge of 2, meaning there are 2 extra electrons. It is 1 carbon atom bonded to 3 oxygen atoms. I realize, actually, that I didn't explain what a covalent bond is. I explained what an ionic bond is, but it's just another type of bond, and that's what bonds carbonate ions together. But then the carbonate ion will bond to typically another metal, and that is an ionic bond. So a little complex perhaps, but hopefully you can understand that. The carbonate ions, like I said, they typically bond to metals. It can be calcium, sodium, even uranium, iron, aluminum, manganese. There are another class just like oxides, carbonates are, and they form what we know as ore. Nitrates are quite rare, and as far as I am aware, they are essentially confined to a desert in northern Chile. They're basically nowhere else on the planet. They are described about the same as carbonates, but a nitrate has 1 nitrogen atom instead of 1 carbon atom, and then 3 oxygen atoms. I actually can't remember what the charge is. It would be -1, I believe. My chemistry is slightly rusty off the top of my head, so forgive me if that's not true. Anyway, nitrates are not as commonly mined today because there are artificial methods of fixing nitrogen to minerals, but the only ones that really matter a lot are known as saltpeter and sodium nitrate. And you may have heard of both of those before, especially maybe saltpeter. I'm sure in other English-speaking countries, or perhaps wherever you learn English, if you're not from an English-speaking country, perhaps it's known as saltpeter is known as niter or something like that. But in the United States, we call it saltpeter, at least where I'm from. Borates are rare and are described as a compound of the elements boron and oxygen, and then they bond to other elements, but it has to include boron and oxygen to be a borate mineral. You may have heard of the cleaning agent borax, and that is one of the most commonly mined borates, but other than that, they don't really matter too much. Sulfates are salts of sulfuric acid, which again would take too long to explain what that means, and they are somewhat rare, but barite and celestite form large deposits which are mined, and you have probably heard of gypsum, which is a sulfate, and it's a very important industrial mineral used for construction. If your house has drywall, then it has gypsum. Phosphates are, as you might guess, salts of phosphoric acid. This is a quite complex group that can form very large crystal formulae, so sort of close to the sulfose salts group. Phosphates are rather important, however, unlike sulfose salts in general, especially for economic activity. Apatite is a phosphate, and it is used extensively in fertilizer production, which obviously is extremely important. And rare earth phosphates are a major source of rare earth metals. A common rare earth metal phosphate is monazite. Finally, we have silicates. All of the other 10 groups I just listed make up about 5% of the minerals on Earth. Silicates make up the other 95-ish%. So, an absurd amount. To quickly sum them up, they are rocks. There are 3 types of rocks that I'm not going to explain here, but they are igneous, sedimentary, and metamorphic. You may have heard of some of those before. Silicates constitute most igneous rock on Earth and significant portions of sedimentary and metamorphic rock as well. Basically, if you go outside and look at a rock or a stone or dig down through the dirt to rock, then it is probably a silicate. Silicate itself is mostly a silicate. Silicate itself is an ion composed of 1 silicon atom surrounded by 4 oxygen atoms. The reason these are so common is silicon is by far the most common element in the Earth's crust, which is the surface of the Earth and what we can dig into. And oxygen is a highly reactive element. That just means it bonds very easily, very readily to other elements. Obviously, this is a very broad group and has many subclassifications as well. Subclassifications can generally be summarized as a group of certain cations bonded to the silicate ion. For example, feldspars, which is a type of silicate, are aluminum and silicates, the silicate ion, bonded together, and in those are bonded to either calcium, sodium, or potassium. And so the calcium, sodium, or potassium would be the cation. Olivines are magnesium or iron silicates, and those are especially important. Minerals are also then further classified into metallic and non-metallic minerals. A general way you can think about this is metallic minerals are ore and non-metallic minerals are rock, though that's not strictly true, but it perhaps simplifies it a bit. Anyway, that was a lot for a quick explanation, but minerals could take a few episodes on their own, and this one is about mining, so hopefully that was somewhat clear. The goal was to have you remember when I bring up a certain mineral type at some point, if I do during the rest of the episode. Also, let me explain real quick what a mineral or deposit is. Ore is rock that contains one or more valuable minerals that is mined for metals or nonmetals or metalloids too. And a deposit is a location where ore has been concentrated from various geologic processes. So it's where the valuable mineral is concentrated inside of the rock. And that rock is more often than not, of course, going to be a silicate, but most of the time, especially for industry to make money in economies, we don't care about the rock on the outside of the ore deposit. We just want to get to the valuable stuff in the center. It's not always in the center, but we don't really care about just the rock. There are a lot of silicates, of course, that are used very commonly in industry. Mostly concrete is made out of silicates, but for a lot of mining, especially metal mining, we only really care about the ore deposit, the valuable mineral that's kind of trapped inside of the rock. Next, I will briefly discuss various machinery used in mining so that if I bring up a type of machine later, I won't have to take a tangent to explain it, and it'll perhaps give you a better visualization about how different mining processes are executed. I promise we'll get to mining itself at some point. Hopefully this section will be shorter than the minerals section so we can actually talk about mining. I'll give an overview of categories of common types of mining equipment without going into specific detail. Mining trucks are, well, extremely large trucks that haul heavy loads of dirt, hard rock, or material, essentially, that's excavated on a mining site, a dig site. These trucks have beds that can hold about 400 tons of material. The key with these trucks is their tires, though, which are enormous. They're roughly 13 plus feet tall, 13 and a half feet tall, 5 feet thick, and the tread is over 3 inches deep. I mean, think about your car tire if you own a car, or just look at a car. That tread is a fraction of a coin, which isn't even an inch thick, so an inch deep. They have to be this large to navigate the rough terrain of a mine while hauling 400 tons of material, though. And these tires alone cost about $42,500 US dollars on average. Hydraulic mining shovels, or excavators, are large shovel bucket excavators that dig and remove tons of material from sites. I mean, these things have massive buckets. Typically, they are on tracks, but some have wheels. They have a comically large looking hydraulic elbow with a shovel, a bucket on the end. And they can move material into trucks and open new dig sites up, as well as just digging. Electric rope shovels are similar to hydraulic excavators in that they excavate material. They are electric instead of diesel. Most hydraulic excavators are diesel. And but they mostly differ in their mechanical function. They use a rope and pulley system to move the shovel bucket instead of using a hydraulic arm. Dragline excavators are another type of excavator, and they have a large crane, so just a rigid crane, and then they have not a rotational bucket, but a bucket that's able to oscillate back and forth, so it can dig up stuff. And so the crane will lower and allow the bucket to scoop material up, and then it'll raise to relocate the material to wherever it needs to go. Continuous mining machines use steel or tungsten gear saw blades, basically, to cut through soft material continuously. They just go and go. These are used extensively in coal mining, and I'll discuss that later and their main uses. They are unmanned machines, and they're sort of like flat beds that are on treads, and they have a conveyor belt underneath that cants sort of upwards towards the back of it. And then the cutting tool is sort of on top of the conveyor belt. Not directly on top, but above it. And so the cutting tool will cut the material, whatever it's digging through, and then it'll drop most of it onto the conveyor belt so it can move it out of the way of the continuous mining machine so it can continue to mine. Blasting equipment is a broad category that sort of describes itself. You can think explosives, basically. These clear out unwanted material in the way of an ore deposit. Electric charging equipment charges explosives or blast charges, and then a remote detonator is used to initiate the blast. Mining drills are contrary to what you might think. There are mining drills that mine ore, but in general, they're too slow and economically unviable, so mining drills themselves are not really used for mining ore. They're essentially only used for creating holes to place blast charges into. Roof bolters are used to support underground mines from collapse. So once a room is cleared out or a tunnel is cleared out, if it's relatively weak or if the room is fairly big, then roof bolters will be able to support the ceiling. They move on treads, and they have hydraulic arms that push against the ceiling of an underground mine to prop up the earth above, in a way, if that makes it easy to think about. Crushing equipment is another relatively broad category, but are on most dig sites, mining locations, but they're also sort of self-explanatory. Typically, a crusher will have a conveyor belt that material is loaded onto, and then run through various types of crushing mechanisms. These mechanisms include gyratory crushers, which they have like a cone head that faces upwards, and then crushes material that's dropped onto the head. Jaw crushers, those compress material between one stationary jaw die and then one movable jaw die that's fixed at an angle. Hammer mills are a wheel onto which hammers are affixed, and then they repeatedly smash the material. I believe gyratory crushers are the most common on site. Mining dozers and motor graders tend to clear material out of the way on a site and level terrain, and wheel tractor scrapers are also used for this. Now, I want to briefly touch on longwall mining equipment, and then we'll move on. Longwall refers to a type of underground mining that extracts material from an elongated wall that's dug out, which can be 2.5 miles long, is the usual length. There is a plow that travels the length of the wall back and forth, and it kind of looks like a large inverted drill head. So instead of like a really large drill head, but instead of it coming down to a point, it kind of starts out smaller and then grows in radius, in diameter. I may post a picture of a longwall mining setup to make this a little easier to visualize. But the plow itself will break the material and whatever it's digging through. And it is attached to a conveyor belt that the material is then dropped onto. And then hydraulic roof supports run the length of the ceiling. This is a very common type of underground mining in mostly developed countries where the local, and then of course where the local geology allows for it, because it is extremely productive and it's almost fully mechanized. So you don't have to have a person actually operating the machine. You just have to have, foremen on the site, kind of making sure that nothing goes wrong. All right, long overdue. What is mining? Seems pretty straightforward, like the rest of the primary sector industries. Well, mining as a definition is fairly simple. It's the extraction of valuable geological materials from the earth. But once the various types of mining are brought up, it gets rather complicated. There are four types in general. You can really put them as two, but I'll describe four, which may not seem like a lot, but each type has various, especially surface mining, has various different procedures and methods. So we'll start with surface mining, as it is the most common. I think it's something like 85% estimated is of all mining on Earth is surface mining. Maybe we like to think of long underground mine shafts supported by pillars and beams of wood with miners in their hard hats and a light and a pickaxe, but I'm sure we can all see how that's pretty impractical today. Open pit is the method most commonly used today, but surface mining also consists of strip mining and mountaintop removal. Surface mining, and yes, mountaintop removal is as bad as it sounds. Surface mining, as the name may suggest, is performed on the surface, where heavy machinery digs out ore. So you can think of all the hydraulic excavators, the dragline excavators, those kind of things. Those are very common in surface mining operations. It is advantageous because there are no tunnels or shafts, and is therefore relatively safer because you can avoid cave-ins, collapse on, especially on your workers. But it is, of course, disadvantageous because of the enormous environmental problems it causes. But more on that later. You've perhaps seen an open pit mine before. It's a large area that is incrementally excavated to create a hole. Over time, the hole grows and it forms sort of an inverted pyramid shape into the ground, with each layer progressively becoming smaller, as to avoid landslide, and requiring each previous layer to have been expanded so the pit doesn't collapse. This is a particularly suitable method for deposits relatively close to the surface of the earth, where the overburden, which is the term used for essentially excess earth in the way of extracting ore, is relatively thin, or if the mineral is occurring in a structurally unsuitable material for tunneling, like gravel or sand. Common ores extracted from an open pit include gold, silver, and copper. Strip mining, on the other hand, is a common method for coal. It is similar to open pit in that overburden is removed and then ore is extracted, but of course no large pits are dug. Only the very top portion of overburden is removed, and then the ore right underneath is extracted. So you don't necessarily have to go as deep for a lot of coal ore, so strip mining is used very commonly for coal. Essentially, weaving valleys are dug out wherever ore is detected, and sort of a crude road system is developed, if that helps you visualize it. As I said before, continuous mining equipment is commonly used in this type of mining because, or at least for coal mining, but especially in strip mining for coal, because it's very efficient for this unmanned equipment to remove the material on top of the ore, and it just kind of keeps going and makes these, kind of road systems, like I said. Mountaintop removal is the final type of surface mining. This is a type that is quite controversial, I would say, because of the destruction of the land. I mean, the other types also destroy the land, but it's easier to refill holes than to rebuild a mountain, in a sense. Mountaintop removal is the literal removal of a summit or a ridgeline on the top of a mountain. It gets removed. Of course, not the whole thing at once. That would be impossible. And then, of course, any ore that exists there would just also get removed. But all vegetation is removed, and then the top portions are blasted away because usually right on top, the overburden doesn't contain any ore. And then dragline excavators are actually commonly used for digging on mountaintop removal. The bad environmental side of mountaintop removal is the common practice of dumping overburden and other debris into surrounding valleys, which further destroys ecosystems and water supplies. And obviously, like I said, you can somewhat relatively refill strip mining valleys. It's not necessarily done very often, or open pit mines. Again, it's not necessarily done very often, but it can be done. While how do you rebuild a mountain? It's basically impossible. You can't do that. The next major category is underground mining, which used to be quite a bit more common during the first industrialization stages. But anyway, there are a couple different methods depending on geology and what is being mined. But essentially, tunnels have to be blasted and then space cleared out underground for any mining to occur. Room and pillar mining is the most common worldwide. It involves a large space being cleared out of a rock face, and then pillars are erected inside the cleared room to support the ceiling. The pillars remain after digging is complete for hopefully obvious reasons. And then, like I outlined earlier, longwall is also common, but it requires very specific equipment and a specific environment. And that's why I outlined it in the equipment section. It's also mostly only done in developed nations, especially because of the equipment requirements. The third major category is placer mining. A placer is a deposit where sedimentary rock layers are exposed to the surface, typically near rivers or streams. And the placer deposit itself is composed of particles of valuable minerals that are washed down rivers as the water runs over the sedimentary rock layers. And then once it reaches a certain location or certain conditions are met, then they form deposits of valuable minerals that are commonly found on stream beds, but they can be found elsewhere. There are various types of placer deposits, which include residual deposits, which form on weathered or eroded rocks where there hasn't been any water for some time, but the deposit also hasn't washed away. Alluvial, these are usually gold deposits. Actually, most placer deposits are gold deposits, but alluvial deposits are found in areas where the water can have washed the material all the way to its end, such as in a valley. Bench deposits, which are deposits on a stream bed, and deep leads, which are it's essentially placer deposits that you have to kind of dig a little bit underneath the stream bed to get to. It isn't very common today, but it does have much less environmental impact than surface or underground mining, but it just doesn't produce nearly the same amount for global demand. But it was the primary source of gold for the ancient world, and is still a pretty good source for gold today. Like I said, placer deposits are mostly gold, because native elements are typically what is mined from placer deposits. But you can also have platinum or diamonds, and then also ore sands that include tin or iron. The fourth major category is in situ mining, which it is Latin, but I'll say I believe it's Latin just in case it's not, but it definitely is Latin, and all it means is on site, in situ mining. It's also mostly called in situ leaching. This method goes as follows. A borehole is drilled into an ore deposit, and then chemical oxidants are injected to dissolve the metal so then it can flow to the surface. It doesn't particularly matter what an oxidant is for the purpose of this episode, but common oxidants include potassium permanganate, sodium persulfate, and what's known as Fenton's reagent, which is hydrogen peroxide that uses iron sulfate as a catalyst. That's probably a lot, but like I said, it doesn't necessarily matter. I just wanted to outline some. Ozone actually is also used, and if you don't know what ozone is, it's 3 oxygen atoms bonded together, and it is the layer in the atmosphere that protects the surface of the Earth from ultraviolet radiation from the sun. Anyway, but we can also create ozone. We just can't create nearly enough to, fill the ozone layer. Copper is very commonly mined in situ leaching. And personally, I think in situ leaching is very cool, and it also causes minimal environmental disturbances like placer mining. Mining can perhaps be claimed as having the longest history, besides maybe fishing, out of the primary sector industries. Flint and ochre are postulated to have been mined possibly 10,000 years ago, and the oldest mine is actually theorized to be over 40,000 years old, and is located in Eswatini in sub-Saharan Africa. Gold was probably the first metal to be mined, and copper and silver have quite a history too, since these metals are relatively stable and can appear in nature in a native elemental form. The oldest industrial form of mining can perhaps be placed in ancient Egypt, where copper was mined along the Sinai Peninsula over 5,000 years ago, and some bronze found in the area is dated to almost 6,000 years ago. Iron was mined as well, though not quite as long ago, and obviously the quarried limestone and red granite used in the pyramids at Giza could be considered industrial activity. At least I would consider it that. Of course, most mining throughout history was a slow and very dangerous process and did not become a true industry until perhaps the introduction of black powder from China. Of course, it could be argued on when it really was an industry, because you have industrialization, the first industrial revolution, and maybe that's when mining first became an industry, but I think it's been an industry for quite a long time, depending on how you define industry. But anyway, black powder, of course, originated in China, but it made its way to the West eventually and was used until dynamite in the mid-19th century. After the first industrial revolution in England and subsequent areas in the West after, mechanical drills driven pneumatically or by steam increased the production of mining several-fold. Just like any other of the industries in the primary sector, mining has extensive history, but today is performed by machines, with miners as trained operators of equipment instead of mostly physical laborers. Especially in the developed world. In the underdeveloped world, there are some physical laborers. The common caricature of a pickaxe miner that still does exist in the underdeveloped world, but to a limited degree. Only the very underdeveloped world. As a point of fact, actually, humans can mine gold today at a depth of over 13,000 feet, and the deepest surface mines have been excavated to over 2,300 feet. Now, I'd like to briefly discuss the apparent mining and energy paradox, since this is rather relevant for today and probably will continue to become relevant in years to come. Decades to come, even. I would imagine most of you know what green energy is, and the push for it in the West, particularly Europe, the United States, and Canada, and probably Australia as well, New Zealand, and perhaps, honestly, even in South America and other countries. After going over various types of mining, you can now perhaps imagine, if you hadn't before, that mining is not very environmentally conscious, despite our best efforts, but we do have to make it economical as well. Solar panels, wind turbines, and especially recently the push for electric vehicles, those all propose a paradox in that all of the material mined to build these things destroy the environment in the process. Not to delve into politics and social science too much, but it is estimated that one offshore wind turbine uses 67 tons of copper, in which 50,000 tons of earth is moved on average to produce that copper. One wind turbine, offshore wind turbine, produces somewhere around 22,000 megawatt hours in a year, and the average US home consumes about 10.5 megawatt hours in a year. So that's about 2,200 US homes from one offshore wind turbine. Not too bad, but then there are an estimated 129 million occupied homes in the United States. So that's all I will say on that. And we will quickly talk about waste before exploring world economies in the mining industry. Waste in the mining industry is generated in large amounts, and it is known as tailings. For most metallic minerals, 1% or less of the desired resource is extracted, while the remaining 99% results in tailings. These tailings can be toxic and difficult to dispose of because of how much is produced. For example, an estimated 1 ton of gold produced results in over 200,000 tons of tailings. So the question remains unsolved. How do we dispose of tailings properly? Well, there isn't really an answer. It just produces too much. Most commonly, tailings ponds are created in valleys close to the mine, since tailings are usually in a slurry form, which is a mixture of insoluble solids and water. It makes it easier to transport. These ponds can, of course, end up causing ecological disasters that are sometimes hard to avoid, especially economically. Various toxins from the tailings ponds end up leaching or being fully released into a local water supply, destroying the ecosystem or potentially ruining a water supply of a nearby city or settlement. The practice of submarine tailings disposal, or STD, is more expensive and it's actually illegal in the United States and Canada, but it is argued to be safer overall than creating tailings ponds. And all it is STD is simply dumping tailings into the sea. It is most commonly used in the developing world, where one can assume environmental impacts of mining are at their worst. Mining waste is classified as sterile or mineralized. It doesn't necessarily matter too much, and it can have acid generating potential, which again doesn't matter too much. This acid, though, will result in further ecological disaster because of the nature of acids. Waste dumps themselves then have to be carefully designed, especially in accordance with the area's seismological activity should an earthquake occur, and rainfall that will leach tailings into water supplies. Hopefully, now everything I have gone over works as a full setup to understand economies in the mining industry across the globe. For this, we will be looking at iron mining in Sweden, Brazil, and Mauritania, which have human development indexes of 0.959 at rank 5, 0.786 at rank 84, and 0.563 at rank 163, respectively, as of quarter 2, 2025. Though, don't expect any of those besides maybe Brazil to change that drastically, even within like the next 10 years or so. As you can see, these three countries have a wide spread of development, with Sweden being one of the highest ranked developed countries, Brazil still on their way of becoming developed, and Mauritania being very underdeveloped. Sweden is a Scandinavian country located in northwest Europe and has estimated usable yearly iron production of 38 million tons in 2023. That is US tons, not metric tons, though they're about the same. Brazil is one of the largest countries in the world. It's actually fifth, I believe, if you count in Alaska and Hawaii, mostly Alaska for the United States. And it's located in northeastern South America and is roughly half of all of the entire continent of South America. Brazil has estimated usable yearly iron production of 440 million tons in 2023, which is second in the world only to Australia. Mauritania is a medium to large sized country on the coast of West Africa, about smack dab in the middle of the bulge on West Africa's coast, if you can visualize that. It is more difficult to estimate the iron production since the country is so underdeveloped, but it is an enormous part of the country's GDP and produced about 14 million tons of iron ore in 2023. I am using usable yearly iron production and iron ore kind of interchangeably. They're sort of the same thing. Basically, usable iron produced is iron ore. It's a form that iron is taken out of a mine after being minimally processed at the mine and taken to be further processed at some secondary sector facility. In iron's case, usually a blast furnace facility or something like that. Anyway, we'll get into that later in a future episode. On the case of Mauritania, it's unclear to me, though, whether or not the 14 million tons number is iron itself or usable iron produced, because they differ since once iron ore is processed, the resulting actual iron is much less than the usable iron or the iron ore that's produced at the mine. I believe it's iron ore, however, especially because it's a lot easier to track how much iron ore is produced versus how much actual iron is produced. But anyway, Mauritania is receiving many grants and investments from other countries, primarily Australia, as many underdeveloped countries do, and they aim to triple production of iron ore by 2030. Before diving into analysis of each of these countries individually, allow me to explain iron ore a bit further. Iron ores are very commonly oxides, as are many ores, and are found in the forms of magnetite, which is 72.4% iron by weight, by mass, and hematite, which is 69.9% iron. Other forms include the hydroxides, which they're technically hydroxide oxides, but we'll just call them hydroxides for our purposes, goethite, and limonite, both of which are 62.9% and 55% iron, respectively. And cedarite is a carbonate with 48.2% iron content. Magnetite and hematite are mined extensively because they generate in typically large veins and are known as direct shipping ore, which means the ore can be fed directly into a blast furnace without processing it further. This topic will become very important in our exploration of secondary sector activity, which results from mining. And then one final note on somewhat secondary sector activity, just to give a scope of what all of this iron is used for. It is estimated that 98% of all iron ore that is mined is used to make steel. But again, much more on that in a future episode, and honestly, there will probably be an entire episode on steel itself. Tailings, or mine waste products, if you remember us talking about that, are rather important in iron mining because there is a relatively high percentage of iron left over in tailings. Nickel, copper, and cobalt are also commonly extracted from iron ore tailings, and these precious metals would all be wasted if not for the careful collection and processing of the tailings, and it is also a helpful practice to reduce the amount of tailings produced from an iron mine. But of course, the primary source of iron comes from the actual ore. Magnetite is magnetic, which the definition of magnetic doesn't matter much for our purposes here, but suffice it to say, it separates from the gangue minerals it generates with easily. I mentioned earlier when I was discussing silicate minerals and ore deposits that most rocks or that ores generated in are industrially useless for the desired product. It doesn't necessarily mean that that is entirely industrially useless, but that is what a gangue mineral is. Whatever mineral is desired for the specific industry. In this case, iron is desired for the iron ore mining industry. Anything else that isn't iron ore is generally going to be a gangue mineral, unless it is easily extracted away from the iron ore. It gets pretty complex depending on the local geology, how ores are formed, and what type of ore it is. But that is what a gangue mineral is, and it's most often a silicate mineral, of course, because silicates are by far the most common in the Earth's crust, on the Earth's surface. And again, this doesn't mean that the gangue mineral is always useless, but it is in general not important because the focus is on the desired mineral. Anyway, this magnetism makes for easy extraction of magnetite ore from the gangue mineral. That's not gang as in, like, gang violence. It's gangue, Gangue. Magnetite is the primary ore mined in Sweden and Mauritania, and worldwide, I believe it is the primary one. So, on my note earlier on Mauritania's production, if it is 14 million tons of usable iron produced, then it is about 9.4 million tons of actual iron. If it is 14 million tons of iron, then it is about 18 million tons of iron ore produced. These numbers are extremely rough, and they rely on 100% magnetite ore mined. because I calculated those numbers from multiplying and dividing, respectively, the iron content of magnetite, which is 72.4%, by 14 million, and then adjusting for a little bit of statistical error. Anyway, hematite is the most commonly mined in Brazil. This is a good ore in general to mine because it generates in high densities compared to the silicate gangue it forms in. It is, however, a bit more difficult to extract because it is not magnetic, as magnetite is magnetic, so a lot more primary processing has to occur to separate the hematite from the silicate gangue. Alright, finally, let's discuss some economic activity based on these three countries. Let's start with Sweden. We will focus mostly on the Kiruna mine in North Sweden, as it is actually the largest underground mine in the world, and it produces roughly 40% of all of Sweden's iron. The iron ore mined is principally magnetite, with a good amount of phosphorus, which is actually not considered gangue. There are large quantities of apatite weaved in the ore deposit located at the mine, however, and that is considered gangue, even though it does have industrial applications. There is also some hematite ore in the deposit, but it is relatively thin and not sought after as the magnetite is. But of course, if some of it generates near enough to the magnetite, then it will probably be mined up. The Kiruna ore deposit was also discovered to be the largest deposit of rare earth metals in Europe, making this an extremely valuable ore body. The Kiruna mine has been operating since 1898 and is considered the largest and one of the most technologically advanced underground mines in the world. The mine is so large that in 2020 the mining activity caused a relatively large earthquake, I believe it was 4.8, and it undermines the local town of Kiruna, and so the relocation of the town is currently underway. Economically, the mine produces over $2 billion in profit annually. It is difficult to find exactly how much the iron mining industry in Sweden produces overall monetarily per year, but Sweden produces over 90% of Europe's iron, as well as a third of the lead and zinc, and close to 20% of gold and silver, and I think about 10% of copper as well. This perhaps helps with the scope of the $2 billion of profit that the Kiruna mine produces, and that is in comparison to the 638 billion GDP of Sweden, nominal GDP. Of course, profit of a single mine can't be compared to GDP, especially because profit and GDP are vastly different concepts. But I will have to do an episode or two on macroeconomics so we can fully understand that. But for now, hopefully that gives a bit of a scope of the absurd amount of iron that the Kiruna mine produces. Sweden has about $12.5 billion in mining export revenue annually, which, after some quick math that I won't explain here, results in about 3.5% of the country's GDP. Iron ore, as with most ore in general across the globe, is transported by train. In Sweden specifically, the iron ore line, or in Swedish, I'm probably going to mispronounce this, but the Malmbanan, transports the ore from the Kiruna mine, away from the Kiruna mine. The ore must be minimally processed into a transportable form, and this is the job mostly of crushing equipment. Once it has been crushed, it is sorted over various screens of different mesh sizes to separate products from larger lumps to finer sands. Then it is stockpiled into large mounds based on size, where it awaits to be loaded onto train cars. This is a general process that one can imagine in almost any iron mine. There are an estimated 7,200 people employed in the mining industry in Sweden today, which is about 0.0007% of its 10.5 million people. Brazil, a developing country in South America, produces an astronomical quality of iron. The country also produces large quantities of many other minerals, but since our focus for this exercise is on iron, let's just appreciate the number of almost 500 million tons of iron ore produced by Brazilian mines. Minas Gerais, I think that's how you pronounce it, one of Brazil's federative units, which is like a state or a province, produces over half of the country's iron ore. What is known as the Iron Quadrangle contains the most significantly producing mines. It is an area inhabited actually by more than 4 million people, and also produces large quantities of gold and gemstones. Pará is another region that produces almost all of the rest of Brazil's iron ore. The mines in this region are so large, actually, that they consist of what are called mining complexes, which are several separate mines grouped into one kind of super mine, if you like. The five largest mining complexes in the country are, of course, located in these two regions, with the two largest, Serra Norte and Carajás Serra Sul, being located at Pará. The other three, Vargem Grande, Itabira, and Paraopeba, sorry, I'm not great at Portuguese, are all located in Minas Gerais. All of the mines in these complexes are surface mines and produce mostly iron ore. There are plenty of other complexes located within the Iron Quadrangle, but the Serra Norte and the Carajás Serra Sul complexes in Pará produce about all of the iron in that region. Economically, north of $10 billion is produced in iron ore annually, and only continues to grow with further technological developments as the country develops further. This is rather significant, as I have read that anywhere between 4 and 7% of Brazil's total nominal GDP of 2.126 trillion as of 2025 is in mining, which puts the industry at a GDP of between 85 billion and 148 billion. Perhaps somewhat arbitrary numbers, but since we are going down the ladder of development in these countries that we are looking at, you will see why this is important once we reach Mauritania. About 0.001%, which is about 200,000 people, 220,000 people or so, of Brazil's population of 212 million work in mining. Yet they are in the top 5 of all mineral-producing countries worldwide, and like I said, are second in iron ore production. Again, the further developed a country becomes, the more advanced the higher sectors of industry become, and less people are required to work in the lower sectors of industry to produce even more out of those sectors. Now, as perhaps has become clear from previous episodes analyzing developed and underdeveloped primary sector activity, even though Sweden and Brazil are distant in terms of their Human Development Index, with the former currently ranked 5th and the latter currently ranked 84th, their primary sector activity in the mining industry is relatively similar, at least in terms of development. Even though they are economically different, vastly, both countries have very small percentages of their populations involved in mining, and its contribution to their respective GDPs is not insignificant by any means, but also the countries would still function if their mining industries were lost. Hopefully that doesn't happen, and I don't know how that would, but Mauritania, on the other hand, is obviously vastly underdeveloped compared to Sweden, but it is about as far away from Brazil as Brazil is from Sweden, at least on the Human Development Index. But since Sweden is a very highly developed country, and Brazil is a highly developed country, even though it isn't technically developed, they do not necessarily require a mining industry to function. Mauritania essentially relies on its mining industry, and it is such an enormous part of the country's economy that one could actually theorize about the types of collapse it would undergo if the mining industry was suddenly gone. Which you will see in a second that it is actually possible for that to happen. Mauritania has a nominal GDP of 10.357 billion by 2025, which puts its per capita income at $2,337. The iron ore mining industry alone accounts for about half of Mauritania's export revenue, which is about $2.2 billion. According to the World Bank, export revenue accounts for 38.3% of Mauritania's GDP, and Brazil's is 18.8%, and Sweden's is 55.2%. So you can see the percentage itself is a bit arbitrary until we examine it against the country's total GDP and where the exports actually come from. Sweden's mining exports account for about 8% of the country's total export revenue, while again, Mauritania's iron ore, not just mining exports, but iron ore exports, account for over half of the country's export revenue, while mining in total is about 76%. If this is a bit confusing, think about to link all these numbers up. Think about the percentages I gave for export revenue as part of the country's GDP earlier. That means that 38.3% of Mauritania's $10.357 billion GDP, nominal annual GDP, is from export revenue, which would be 3.967 billion. Now take about half of that, about $2.2 billion, as I said before, and that is Mauritania's iron ore export revenue total, which is then about a quarter of the entire nominal GDP of the entire country. It would then be reasonable to conclude that if something failed in Mauritania's iron mining industry, that the country would face economic collapse. This is not something that is possible in developed and even most developing countries, but it is certainly possible in the world's poorest and generally most underdeveloped countries. I said earlier that Mauritania produces upwards of 14 million tons of iron ore annually, and there is actually one single mine in northern Mauritania near the town of Zouarat. I believe I'm pronouncing that correctly, which produces upwards of 13 million of that 14 million tons. There are 3 enormous iron deposits here, mostly of magnetite, and there is a single train line that runs 6 trains daily, 3 empty and then 3 full, that carry almost 19,000 tons of ore each. These run 700 kilometers from Zouarat to a port in this one I really don't know how to pronounce. I researched it, before the podcast, but I've since then forgotten how to pronounce it. Nouadhibou. I'm very sorry about that one. Nouadhibou. Nouadhibou? We'll go with Nouadhibou. And this railway is owned by and operated by the company with a majority stake in the mine. The company is abbreviated SNIM, which means Société Nationale Industrielle et Minérale, which is French, if you couldn't tell. The French occupied Mauritania until 1960, so the influence is quite heavy. This is a Mauritanian government majority-owned company that is managed by Arabian financial and mining organizations that I couldn't find the names for, so perhaps they want to stay hidden. Anyway, all of this is to say that Mauritania's economy relies essentially on one thing, and can be traced to one other thing, that can then be traced to one other thing, sort of in a line. So it's a very fine balance, and this kind of scenario is again more common than one would hope in severely undeveloped countries. A silver lining, though, of sorts, is that Mauritania has near exponential room to grow the industry if it's handled correctly. This could, of course, prove to be a boon to the country. Now, there is more I could discuss here, but I do think this episode has probably run for long enough, and I don't have enough content on the foundations of the mining industry for an entire new episode. Things I wish to discuss there will most likely appear in future episodes, however. Anyway, if you enjoyed the episode or want to send critiques, suggestions, or whatever, please feel free to send me an email at fabricofindustry@gmail.com or visit the website at fabricofindustry.podbean.com. Visit the Facebook page as well. I've set up a Facebook page finally by searching Fabric of Industry, and give us a like and a comment if you would. It helps spread visibility so more can enjoy this content and learn. I also have a Discord server as well that I can send a link to through email until I find a better way to distribute it without it having it become full of scammers. You can find the podcast on any major podcast aggregator you like best, be it Spotify or Apple or YouTube, and reviews there would be much appreciated as it also helps spread the podcast. As always, thank you for listening, and I hope you enjoyed, and I'll talk to you next time.